right, hi everybody. So what I'm going to do today is basically go over some stereochemistry stuff. All right, thanks, Tim. All right, so we're going to go over a little bit of stereochemistry stuff. Obviously, I'm wearing this goofy headset because I'm trying to also stream this on YouTube so that if any of your classmates who couldn't make it today want to watch it, they have an opportunity to do so. What I wanted to start with is by briefly going over stereoisomers, okay, in general. All right, and then after we go over stereoisomers in general, then we'll look at the actual problems, the actual homework set that you have to do, the pre-lab questions, okay? So basically when you leave here today, you'll be done with your pre-lab, you'll have all the right answers, hopefully, unless I screwed up, but basically we're gonna go over this. There are a couple things I wanna remind you about. We once again moved back the assignments 3 and 4. They're not due this week, they're due next week, all right? And we also upgraded the software in the cell. I know a few people had issues with that. So we upgraded it so it matches exactly the stuff that you find on the video, okay? And that's basically what we did. Also, we noticed that a number of you didn't do your post-lab questions. So if you want to do your post-lab questions for the first experiment and you didn't do so already, please turn those in when you go to lab this week, all right? And you'll get full credit just as if you turned them in. From now on, please make sure you do the post-lab questions. For whatever reason, they're at the end of the lab manual. I think that's because it makes it easier for us to edit them, but we can maybe change that in the future, all right? During class this week, you're going to take a quiz during the first 15 minutes. You probably saw, but there's a practice quiz available to you. You can download the practice quiz. You can also get a copy of the practice quiz, the answers, and me going over the questions on YouTube. All right, and I sent you a link to that in the announcement today. So if you want to do that, go for it. All right, last thing is about what we're actually doing this week. So this week's experiment is a stereochemistry experiment. It's not an experiment, right? It's just paperwork. So basically what you're going to do is you're going to get 20 points for doing the pre-lab, which we're going to do in 5 minutes or 10 minutes from now together as a group. And obviously if you watch this video, you can just get the answers from there. But it's important to know how to do it. Then you're going to spend about an hour and a half, okay, doing some problems that are right in the lab manual as a group. You can work with your classmates, you can use your book, you can use the internet, whatever the case may be, whatever you want to use, you can use, and you basically get a feel for these types of problems. And we're hoping this will help you in the lecture course because this is part of the lecture course. Then finally, what you're going to do is you're going to do like an individual thing, and that's 40 points. All right, so you get 20 points for doing the pre-lab, you get 40 points for doing the group work, which there's no reason you shouldn't get all the 40 points for that, and then you get up to 40 points for the individual thing, which is based on the group work, all right? And honestly, it's based on the pre-lab too. They're all kind of the same, just different examples of the same stuff, all right? So that's basically how the lab is gonna work this week. It is all paperwork, so you don't need to have your goggles or your lab coat or any of that kind of stuff, because it's just paperwork. All right, so now that we've talked about all the administrative stuff, let's talk about actual stereoisomers, okay? So what is a stereoisomer? Okay, so the stereoisomers that we're going to talk about mostly today are enantiomers and diastereomers. And enantiomers and diastereomers are basically going to be a different three-dimensional arrangement of atoms. So for example, if there's a bromo group on the 3 carbon or a bromo group on the 4 carbon, that's a constitutional isomer, right? You could have bromopropane where it's 1 bromo or 2 bromo propane. Those are constitutional isomers. But if the bromo group is on the same carbon, you can still have isomers, okay? In the case of propane, you can't. But in the case of butane, you can. So 2-bromobutane can have isomers that are not differing on where the bromine is. And those are the stereoisomers that we want to talk about. So basically what we can do is we can group isomers into kind of all isomers. And the first type, okay, are the ones we were just talking about, and they give the example of fluoropropane. I was saying bromopropane, but here you have the fluorine on the 2 carbon, and here you have the fluorine on the 1 carbon. These are constitutional or structural isomers. They're technically not stereoisomers, okay, but they are isomers. So if you look at this kind of hierarchy of what's going on. Now, as you just said, stereoisomers are spatial isomers. So if we look at this example here, we have a carbon bonded to a fluorine, a chlorine, a bromine, and a hydrogen. Okay, and there are 2 configurations of that. that can exist. And those two configurations are labeled as what? We're not going to do it for this one, but we'll get to it eventually. In this case, it's R and S, okay? You can have the R isomer, the right-handed isomer, or the S isomer, kind of like the left-handed isomer, but you can have R and S configurations of these enantiomers. Then there's another type of stereoisomers, which are called diastereomers. And there's one that you're already familiar with, all right? Those are your cis and your trans diastereomers. Why? Well, these don't differ in arrangement, right? These are both 2-butene, one cis and one trans. The atoms are all in the same order, but a double bond, in the cis case, you can have the 2 methyl groups on the top, or in the trans case, you can have one on the top and one on the bottom. So one on the top, one on the bottom. So these are a type of diastereomer. There's another type of diastereomer, and those are diastereomers which contain multiple chiral centers. And these can be one of the more challenging ones to identify because atoms with multiple chiral centers can either be diastereomers, they can be enantiomers if they happen to be mirror images of each other, and they can also be, of course, the same molecule, right? Just written differently. So these are among the most challenging because they give the example here of 2-bromo-2-butanol and 3-bromo-2-butanol, and they show all of the different examples, the ones that are enantiomers, the ones that are diastereomers of each other, and these are diastereomers of each other as well. So multiple chiral center atoms, again, can be different types of diastereomers. So before we talk a little bit more detail, this is kind of just like the hierarchy of the types of stereoisomers that exist and how they differ from constitutional isomers. What we want to talk about is why. Why does this exist anyway? Okay? And the reason that this exists anyway is because of how essentially nature works. So the most common example of things that are chiral, okay, are your hands. All right? Your hands are mirror images of each other. And they look functionally very similar. But if you've ever tried to take a left-hand glove and put it on your right hand, you quickly realize your hands are different, right? One moves in one direction and one moves in the other direction. So although they're mirror images of each other, they're not exactly the same thing. And it turns out that molecules are the same way. So molecules, even though they could be mirror images of each other, they may not be exactly the same thing. And sometimes they are and sometimes they aren't. So we tell you this, stuff like molecules, if they're non-superimposable mirror images, then they're enantiomers. But that doesn't really help you to figure out, is something an enantiomer? All right? So how do you practically figure out if you have a chiral center? Other than just saying they're non-superimposable mirror images. That's exactly right. When carbon is connected to 4 different groups, it will have a right-handed version and a left-handed version. That's just a fact, okay? Just like your right and left hand are mirror images. All right, I have a 6-year-old. We build Legos, all right? You'd be surprised how often chirality comes up with Legos. You're building a guy or whatever, and it has a right leg and a left leg. And if you put the Legos backwards, right, they're made out of the same pieces, then you get 2 right legs and you can't put it together at the end. So knowing about mirror images actually comes up when you're building Legos. But let's look here at why this is the case, okay? And what I have here, and I'm going to try to keep these on the camera, so you're going to have to look up there as opposed to looking at me. Let's look at these different situations. So what I want to do is, I want to take these molecules, okay, with 4 different balls on them. And essentially what I want to do is turn them into mirror images. All right. So these are now mirror images. The mirror plane is where my hand is. So yellow lines up with yellow. Green lines up with green. This is an orangish color in it looks a little red over here, but it's orangish in real life. Orange lines up with orange, and red lines up with red. So these are mirror images. You see that? Now, let's see if they're superimposable. All right? So all I want to do to superimpose them is, I want to line red up with red and orange up with orange. You'll notice that green and yellow don't line up. So let's line up green and yellow. All right? So now I line up green and yellow, and what you'll notice is red and orange don't line up. And no matter how I rotate this, if they are mirror images, they won't line up. All right? Now, let me just prove the point. So let's take this and rearrange it. All right? Now, everything lines up. Red and red, orange and orange, green and green, and yellow and yellow. All right? Now, let me try to make mirror images. Well, in this case, I have red and green lined up. But you'll notice yellow is across from orange. They're not mirror images. All right, so let me fix that. Let me make it so yellow and orange are lined up. Now yellow and orange are lined up, but if you look, green and red are not mirror images. So if you have 4 different substituents, you definitionally have non-superimposable mirror images, just like your right and your left hand. One last thing I want to do quickly to prove this to you. Let's put 2 balls that are the same. So now all I did was I took out the, oh, I did that wrong. All right. So now I took out the same group, which is more effective. All right. Now let's look. I now have mirror images. I took out both the red balls. So I have yellow with yellow, yellow with yellow, orange with orange, and green with green. So these are now mirror images. Now, let's see what happens if I try to line them up. I can easily line them up. So if the molecule isn't bound to 4 different things, I can line up all the groups. So I can make both mirror, not like that, all right, mirror images, and they still line up. So when you're looking for chiral carbons in this course, or in organic chemistry in general, you're looking for something bonded to 4 different groups, because that just happens to be in nature how you can have 2 different spatial arrangements, or how you can have non-superimposable mirror images. All right, so now I want to switch back over to this. All right, so here's 2 different groups. Couple things we need to know about 3D versus 2D representations, because this will come up when you're actually trying to determine whether something is R or S. And that is that anything that's written with a solid line like this, okay, means in the plane. In this case, in the plane of the screen you're looking at, or the screen you're looking at. Okay, so this means in the plane. This wedge, or excuse me, this dashed thing here means sticking back, sticking away from you. And the wedge, the darkened in one, means sticking out or in front of the plane. And if you build these 3-dimensional structures, what you'll quickly realize is you can always get 3 atoms in the same plane. Okay, so these 3 atoms are in the same plane. One is sticking away from me, and one is sticking toward me. And that'll always be the case if you actually build the models. So by putting 3 atoms in the same plane, one will be sticking out and one will be sticking in. All right, if you have a chiral center. So it's really important to know which is which, because it matters when you're actually determining the arrangement of the atoms. Now, why do we draw it like this? Why do we have to do this? It's a practical reason. How do you draw something on a board in 3 dimensions? You don't, okay? Because the board is 2 dimensions. The paper you're going to write on is 2 dimensions. So we need a way, an accepted way, of drawing something that's 3-dimensional in a 2-dimensional space. So you just have to memorize this, all right? Or you have to know it. So that's basically that. So now let's look at this same atom, which is chiral, because it's bonded to 4 different groups. You'll notice it's bonded to a hydrogen, a fluorine, a chlorine, and a bromine. Okay? So it's bonded to 4 different groups, so therefore it is chiral. And we want to determine if it's R or S. What you need to do is rank the groups by molar mass. Okay? The higher the molar mass, the higher the priority. And we'll get to some more complex ones in a couple minutes when we go over the example. So in this case, bromine is first priority because it's higher in molar mass, then chlorine, fluorine, and hydrogen is fourth priority. Okay? So that is how we're going to rank them. So basically 1, 2, 3, and then we put the lowest one back. Is the lowest priority group back in this case? Yes, because the hydrogen is on the dashed line. Dashed, remember, means away from you. Note that if you look at these enough, you'll actually see it. I actually see that as pointing away from me. Okay? But it takes practice to be able to do that. So we rank the groups 1, 2, 3, and this one is 4. We then determine whether it's clockwise or counterclockwise of a rotation. So if we go 1, 2, 3, that's the same way that a clock goes. That is the R configuration. A good way to remember this is R is for right. If you wanted to turn your car right, you would turn your steering wheel clockwise. All right, so if you ever forget that, R is the same as turning your car right. All right, on the road. And then S is left on the road. All right, let's look at the other one. Note that all I did was change 2 groups. I put the fluorine here and the chlorine here. So I flopped these over. Fluorine's here, chlorine's here. If you switch any 2 groups, what you're going to realize through time is, as you practice these, you definitely switch the enantiomer. So just by switching them, you switch the enantiomer. However, let's take a look. Bromine is still 1, it's still the heaviest. Chlorine is still 2, it's still second. And fluorine is still the lightest, other than hydrogen, which is pointing away from us. We now have 1, 2, 3. This is counterclockwise, or the direction you would turn the steering wheel to turn your car left. This is the S configuration. All right, so this is how we determine R and S. So we rank the groups in terms of their molar mass. You did this before when you were determining E and Z, yes? On a double bond, whether it was cis or trans or E and Z, you rank them in terms of their size? You haven't even gotten to that. Okay. All right, and you definitely haven't gotten to this, right? How many people in this room have not gotten to this? All right. You haven't? Not in class. All right. All right. So we're a little behind we're a little behind. All right, or we're a little ahead. I should say we're a little ahead. The lecture isn't necessarily behind. All right. Last thing is meso. Meso is weird, and it means there's an internal plane of symmetry. And the only way that you're going to see a meso compound is if you make the model and you flip it over like a pancake. All right? What you're going to find is if you make a compound like this, where this is S and this is R, and you take it and you just literally flip, I can't really show it, but you flip this end over here like a pancake, okay? What you're going to see is you turn it into RS. Said another way, if a molecule has an internal mirror plane, okay, this internal mirror plane where OH is here, carboxylic acid is here and here, H is here, and carbon is here and here, then the molecule is meso and it is not chiral. All right, and again, the only way to see this is to build the model. This comes up a lot if you're studying biology and you're studying specifically carbohydrate chemistry, okay? Because these are carbohydrate-esque, right? These are oxidized versions, but they're like carbohydrates, all right? So this is basically in 8 minutes, okay? All there is to know about stereoisomers, all right? I thought more of you had this. My understanding was there's only a few of you who hadn't had it, so I apologize for that. All right, now let's do the actual pre-lab. And you're going to have to bear with me for 1 second because I need to zoom this in, which is a manual process. All right. All right. So the first thing we want to do is determine whether the molecule is chiral or achiral. What page is this on in your lab manual? Okay, so this is on page 83 of the lab manual, so you can actually just, do this and rip it out. All right, so we want to determine whether it's chiral or achiral. What does chiral mean again? Is there a carbon with 4 different atoms attached to it? Okay, and if we look here, I believe this in this molecule here, okay, we have this ring, the ring going in this direction, and OH, and what else is here that's not shown? Hydrogen. Which direction must that hydrogen be in? Back. It must be back, right? Because there's already three things in the plane. This carbon, and essentially this carbon are in the plane. So if this is sticking out, that's got to be sticking back, and that's hydrogen. All right, same thing on this one. Now, normally you would say that this is chiral because you have two atoms with four different groups. However, this specific one is not. And we threw you right in the deep end of the pool with the first question. Okay, why is this specific example not chiral? You have an internal plane of symmetry. In fact, it's right there. So this half of the molecule is the mirror image of this half of the molecule, which means that if you were actually to build this and flip it over, you'd get the opposite. An enantiomer, said another way, it's the same molecule. It's not the opposite of an enantiomer, it's the same molecule. So this is a meso compound and is therefore achiral. All right, so this one has an internal plane of symmetry, is meso and achiral. All right, example number 2 is a more straightforward example of this. It says, is the molecule below chiral or achiral? Okay, so let's take a look. What are we looking for to determine whether it's chiral or achiral? 4 different substituents. Okay, so here we have a carboxylic acid. What do we have here? OH group, what do we call that? Alcohol, carboxylic acid, and a hydrogen. What do you think, chiral or achiral? Achiral, why? There's 2 carboxylic acid groups, all right? These 2 groups are the same. This does not have 4 different substituents. This is like the model we made with the 2 yellow balls on each model. This is achiral, all right? So this one is achiral. Next question. I'm going to have to fold the paper here to make this fit. It says, which of the following term best describes the pair of compounds shown? Enantiomers, diastereomers, or the same compound? Okay, so enantiomers are going to be where they're non-superimposable mirror images. Diastereomers means 2 or more stereocenters. They're not cis and trans. So 2 or more stereocenters that are not mirror images. And the same compound means they're both the same. Okay, so we need to figure this out. In this case, how many chiral carbons do we have? 2. This is a chiral carbon, and this is a chiral carbon. What is sticking off of this chiral carbon? A hydrogen. Is it sticking away from us? Is it in the same plane, or is it sticking towards us? It's going away from us. How do we know? Because this one is towards us. These 2 are in the same plane. All right, so I'm just going to put it there. Now we have an OH. This is also a chiral carbon. There's also a hydrogen attached to this one because it's only got 3 bonds, right? To OH, to this group, to this group. So there's a hydrogen. Is it sticking away from us, towards us, or in the same plane? This one's sticking towards us. Okay, so that is basically that. Now, in order to solve this problem, believe it or not, it's kind of a lot of work. What we need to do is we need to figure out whether this is R and S, R or S, and whether this is R or S. And then we need to compare it to this one. Okay, so that's basically what we're attempting to do here. So what do we need to do to figure out whether something is R or S? Prioritize the groups, all right? What is the highest priority group? Well, generally speaking, what's the highest priority group? The one that's the heaviest. So what you want to do is you want to go one atom at a time until you find something different. Clearly on both of these, what is the lightest group? H, right? Hydrogen has a molar mass of 1. It's always the lightest group, all right? If there's 2 hydrogens, it's not chiral. So hydrogen, if there is 1, is always the lightest group. So let's go one atom at a time. If I go this direction, I get a carbon. If I go this direction, I get a carbon. And if I go this direction, I get a carbon. It's a 3-way tie. Okay? And I'm doing this kind of the long way. Once you do a few of these, you won't have to do it this painfully slow, but this is just kind of showing you what we're doing. Now that I'm at a carbon, the next heaviest atom I can get to is a hydrogen. Here, I'm at a carbon. There are, of course, 2 hydrogens here. But the next heaviest atom I can get to is a carbon. And in this case, I'm at a carbon, and the next heaviest atom I can get to, there's a hydrogen and a carbon, is an oxygen. So since oxygen is heavier than carbon or hydrogen, this is priority 1. In this case, since carbon is heavier than hydrogen, this is priority 2. And in this case, this is priority 3. And hydrogen's priority 4. I'm just going to not write that. Okay? Now, it's very important to remember that when you're assigning the R and the S configuration, you have to be holding the hydrogen, or the lowest priority group, in this case hydrogen, away from you. In this case, the hydrogen is already away from us. So we're good. So we have 1 to 2 to 3. Is that clockwise or counterclockwise? That's clockwise, or the same that you would turn your car right if it was a steering wheel. So this carbon with the methyl group, I'm going to label it as CH3, and I'll label the other one as the OH, is R. Okay, I should have mentioned these are both 2-methyl cyclohexane 1-ol. All right, so these are the same molecule. They're not constitutional isomers. All right, now I have to do the same thing for this carbon. In this case, the highest priority group is the oxygen, right? Because oxygen's heavier than carbon or carbon. All right, now if I go to this direction, I have a carbon, and I can get to 2 other carbons. If I go in this direction, I can get to a carbon, and I can only get to 1 other carbon and 2 hydrogens. That makes this group to the left, and it's getting messy in here, carbon 2. And this group down here, carbon 3. Now I go and I look at my rotation. Is that clockwise or counterclockwise? 1, 2, 3. That's counterclockwise, okay, which looks like S. But there's a problem here. Does anybody know what the problem is? The hydrogen's sticking out at me. So if the hydrogen is sticking out at you, you actually have to reverse that. I could not more strongly recommend that at first you build models of these things. Because if you build models, you'll see it in your head. I can see this in 3-dimensional space, but only because of practicing it for a while. So this is actually R. So with respect to the OH, this is R. Okay. Next, we're looking at this molecule right here, and we want to label the groups. So in this case, I have a hydrogen. Is it sticking out at me, or is it away from me? This is away. And in this case, I have a hydrogen that's it's meant to be a wedge sticking out at me. Okay. Now, we've already prioritized. It's the same groups, so we're just prioritizing again. With respect to this carbon, this is 1, this is 2, and this is 3. Okay. 1 to 2 to 3. Is that R or S? That's S. That's counterclockwise, or how you would turn your car left. All right, if you turn the steering wheel in that direction, you go left, that's S. Do I need to flip it, or could I keep it as S? Keep it as S. So CH3, with respect to CH3, it's S. So this is for this one, and we'll do this one over here. All right. Now, let's look at this one. This is 1. This up here is 2. And this over here is 3. So we go 1, 2, 3, like that. Okay? Is that R or S as written? That is R. That is clockwise. Okay? Or turning the car right. Do I keep it the same or do I flip it? So this is R, but it becomes S with respect to the OH. Now, this is a very hard question if you haven't had this before. This is pretty much an impossible question. But now that we've figured out the configuration, this one is both R and this one is both S. Do you know if they're enantiomers or diastereomers? They're definitely not the same molecule, right? They're actually diastereomers, okay? Again, we threw you right in the deep end of the pool, giving you the hard ones right off the bat. They're actually diastereomers. No. What am I talking about? They're actually enantiomers because they both switched, all right? If they both switch, sorry about that. If they both switched, so this one's R, this one's R, this one's S, this one is S. If they both switch, then they're enantiomers. If this had been RR and this had been RS, so only one switched and one stayed the same, then they're diastereomers. All right? And obviously if this is RR and this is RR, then they're just the same molecule. So it's a lot of work to figure out what the configuration is. You actually have to figure out whether everything is S and R, S or R. All right, let's do another one. In this case, it says label each chiral carbon in the compound below as R or S. So this is an easier example and probably should be first, but that's okay. All right, so we need to label this as R or S. So I've already labeled the chiral center, and you can actually, not so much on the screen, but on the paper you can see what it is. All right, so what do we need to do in order to determine whether this is R or S? Prioritize the groups. All right, so our choices are a methyl group, an OH, this thing, or this thing. So going in this direction or going in this direction. What is clearly priority 1? OH, because oxygen is heavier than carbon, and in all other directions, I hit carbon. Now, if I go in this direction, I hit a carbon and then hydrogens. So this is the lowest priority group, all right, which is good because it's already sticking away from us. Note that the lowest priority group doesn't always have to be hydrogen, right? It could be, in this case, a methyl group. It can be lots of different groups, but in this case, it's a methyl group, okay? Sometimes it's hydrogen. Now, if I go in this direction, I then hit a double bond. And if I go in this direction, I just hit single bonds for a while before I hit that double bond. Which direction do you think is higher priority, the double bond or a bunch of single bonds before I get to the double bond? The double bond. The double bond is priority 2 because from this carbon, I can essentially hit 2 other carbons, if you will, because it's double bonded. In this direction, I can only hit 1 other carbon and 2 hydrogens. Note that that only comes into play if they're a tie, right? If this had been able to go to some bigger atom, then you wouldn't have to worry about that. So I get 1, 2, 3. All right? So 1, 2, 3, like that. All right? Is that R or S? That is the S configuration, right? That's counterclockwise. Do I need to flip it, or can I just keep it S? Keep it. Why? Lowest priority group is already in the back. All right? So this is the S configuration. All right. Next one. It says, draw the, oh, that is the answer. All right. I accidentally printed the answer key. All right. It says, draw the structure of S, 1 bromo, 1 chloro, propane. All right. Take care to indicate the 3-dimensional stereochemistry properly. Note that this is very similar to what you have to do for your molecule project if you have a chiral carbon. So you actually have to draw it yourself, which, as I showed you, that ChemSketch actually does it for you. However, we want to draw 1 bromo, 1 chloro, propane. So the first question I have for you is, what is propane? C3H8, or it's a 3-carbon chain. So I'm going to draw the skeletal formula of a 3-carbon chain like that. Okay. Now, on carbon 1, I need to put a bromo and a chloro. And I want to make this S. All right? So, what else is going to be on carbon 1 besides a bromo and a chloro? A hydrogen. All right? Right? Because there's got to be 3. This carbon has 1 bond to carbon, so it's got to have 3 other bonds. So it's got a bromo, it's got a chloro, and it's got a hydrogen. To make my life as easy as possible, what group do you think I should put to the back? The hydrogen, because it is the lowest priority group. So I don't want to have to flip it. Why would I do that to myself? Well, I'm going to make my life as easy as possible. So what I want to do is I want to put the hydrogen to the back. Now, if it were me doing it, I would put the bromine to the front, because you got to put something to the front. All right? So I'm going to put the bromine, the highest priority group, to the front. Now, I have 2 choices, right? First of all, which plane does the chlorine have to be in? The same plane as the paper. Said another way, it has to be drawn with just a straight line. Okay? So I have 2 choices. I can either put the chlorine here, or I can put the chlorine here. Said another way, I can put it on the left side of the bromine, or I can put it on the right side of the bromine. Well, how do I decide what I want to do? I want this to be S. So this is group 1, right? This is group 3. Do I want group 2 here or group 2 here in order to make this in the S configuration, the counterclockwise direction? Do I want it to go this way or do I want it to go this way? First way or second way? The second way. So I put my chlorine here. Now I have the S configuration. All right, everybody see how I did that? So I put the hydrogen back to make my life easier. I put the bromine forward. It didn't really matter. I could have done the same thing with the chlorine, but I put the bromine forward, and then I just decided where to put the chlorine, either here or here. All right, this can be challenging because you're not actually doing it. You have to draw it yourself. All right. Sure. One, two, three. You see it? Okay. All right. So now we're getting to possibly an easier question. It says, how many chiral centers does the following molecule contain? What are we looking for again if we were trying to identify chiral centers? 4 different substituents, all right? A big hint that this is a chiral center is somebody drew it like this. I will warn you, your textbook will do things like draw non-chiral carbons like this. That's not technically wrong, right? Because all the carbons are tetrahedrons and in 3-dimensional space. Chemists won't do that to each other, but they'll do it to students, all right? I don't know why that is. All right, so let's look at this carbon. It's bonded to the ring in this direction and the ring in this direction. Is that different? Yes, because in this case, you have to go 2 bonds before you hit a double bond. And in this case, you have to go 1 bond before you hit a double bond. Note that if this double bond were here, that would not be a chiral center. So if you had something that looked like this, that is not a chiral center, because now this direction and this direction are identical. But in this case, 1 bond is a double bond, 2 bonds is a double bond. Those are different. And of course, this isopropyl group is different than hydrogen. So this is a chiral center. The other option for a chiral center that I can see is here, right? This is a CH2. These are double bonded, so they can't possibly be chiral. This is a CH3. So the only other possibility is this one. All right, what do you think? Chiral or not? No, why not? Because it's attached to 2 methyl groups. Note that if this is an ethyl, now that's a chiral carbon. All right. If this group and this group are not the same, this whole thing is certainly different than any of those and hydrogen. So then it would be chiral. But because these are both methyl groups, in this particular case, there's only one chiral center. All right. Finally. And I apologize for printing out the answer sheet. So I had to cross them out here, but it says, label each chiral carbon in the molecule below as having an R or S configuration. Okay, so we have this one first. All right, so in this case, this is a very challenging one to figure out as far as priority groups. What is clearly the lowest priority? Hydrogen. And what do you notice about that hydrogen? It's sticking out at us. So whatever we get, we're going to have to reverse. Okay? So whatever we get, we're going to have to reverse. However, we have this group sticking here. Then we have the carboxylic acid, and then we have a carbon bonded to a fluorine, and then we have all this carbon stuff over here. Okay? So what do you think is the second or the first highest priority? The carboxylic acid or this group over here? Believe it or not, it's actually the F. Why? In this case, I go one carbon and then I can get to an oxygen. In this case, I go one carbon and then I can get to a fluorine. What's bigger? Fluorine. So this is actually priority 1. All right. 2 is the carboxylic acid, and 3 is the group that just contains carbon. So in this case, it's 1, 2, 3. As written, is this R or S? It's written as R, right? This is clockwise. However, what do we have to do? Flip it. Whoops, I don't know why I did that. R becomes S. Not 8, it becomes S. All right? So R becomes S because the hydrogen is sticking out. Now, because we really wanted to throw you guys in the deep end of the pool, we gave you this one. This is a problem. This is a problem because the hydrogen is not either towards us or away from us. It's in the plane. So we can't necessarily count on the fact that we can just reverse it. You can count on the fact you can just reverse it if the hydrogen is sticking out towards you, right? Because then you're just literally grabbing the molecule and flipping it upside down to get it to stick away from you. However, here you can't count on it. So here's the trick. The trick is to take the group that's sticking away from you and make it the lowest priority group, in this case, hydrogen. And take the group that was hydrogen and make it the group you just canceled out. Like that. All right? If you flip any two groups, you reverse the stereochemistry. So I made hydrogen away from me, but whatever I get, I got to reverse it because hydrogen was originally in the plane. All right? But this will save you from having to make the model, but I do, again, recommend you make models until you can see this. All right? So now we need to prioritize our groups. We have a methyl, we have an ethyl, and we have this whole large group. All right? What do you think is priority 1? The large group, the ethyl, or the methyl? The large group. That's 1. All right? Now, what's 2? The ethyl or the methyl? The ethyl, because in this case, I get to a carbon and then another carbon. In this case, I can't get to another carbon. So then, of course, the methyl is 3. We now have 1, 2, 3, like that. Is that the R or the S configuration? It's kind of messy there, but it is the R, all right? That is clockwise. But what do I need to do? Reverse it so that it's S. So this one, it's really messy here, but it's S on this side, if you can see that, and S on that side, but I wanted to show you how we did that. All right, so that's kind of a crash course in how to solve some of these things. On the plus side, I know there's not a lot of plus side here because we're a little bit ahead of you where you are in the lecture, but it will help you when you get to the lecture to kind of understand, hopefully, what's going on. So I appreciate you coming today and watching this. And if anybody has any questions at the end, I'd be happy to answer them. I'm going to turn this off, though.